So, as I was saying, I can just tell the student, are you ready to take to take the strokes of the cane, or I should keep it to myself? Okay. So that's the kind of that's the way it looks, or that's the way it appears. It appears very, very dubious and confusing when you actually write or an answer, or you produce an answer without specifying the unit. It is when the units are specified that it begins to make sense. That is when it actually makes sense. For instance, if I just tell you that the height of the man is 2, that does not make sense. Is it 2 meters? Is it 2 feet? Is it 2 inches? Whatever. Do you understand that? So that is when you can say that this thing actually makes sense. So there's need for you to tell the quantity, or say the magnitude or size of the parameter, and also specify its units, okay, in the list. That's what you need to specify. Of course, later we'll talk about scalars and vectors, and we'll see another parameter, that's another thing you have to specify about some quantities, okay. But for now, magnitude and the unit, they are actually very, very essential. All right, so before we begin to list the fundamental quantities and their units, and also talk about some derived quantities we can think of, there are different ways you can actually make measurements, okay, as have been presented here. You can have what we call direct measurements. You can have what we call a direct measurement, and you can have what we call an indirect measurement. So in the case of direct measurement, you are making a direct comparison, okay. You're making a direct comparison between two elements. So you want to measure two, you want to see how big is one, or how small is one relative to the other, okay. For instance, you may want to measure how long. Maybe I want to measure how long this book is. If I want to measure how long this book is, I can make a rough estimate by comparing its length with that of this pen, and say, okay, this is almost 1.5 the length of this pen. Okay, that is what we mean by direct measurement. So you are making a direct comparison between a particular length that is already known, or a particular quantity whose magnitude is already known, and another whose magnitude is to be known. All right, so that's what we usually do when you use a ruler, for instance, to measure length. You already know the length of the ruler based on the gradings, that's the marks on the ruler. So you are now trying to do a direct comparison between the length or the grades on that ruler and a particular object that you want to measure. For instance, this is a ruler. I already have these graduations or scales on the ruler, so I know from this point to this point is 1 centimeter. So I'll now do a direct measurement, or place it here and compare. I want to compare the ruling here and this length. So that's what I mean by a direct measurement, okay, of a parameter. All right, so that is that about that. But in the case of, look at the case of for instance, when you talk about a clock, for instance, in the case of a clock, you are not doing a direct measurement. It's not that you are trying to place a clock here and you are trying to compare it with something else. In the case of a clock, you are trying to use a law or relationship between the moving components of that clock, and how long it will take them to move compared to the actual event you are doing. So in that case, that does not constitute a direct measurement, okay. So in the case of direct measurement, you are comparing the size with another of the same species, so chosen as the sample. All right, and in the case of indirect measurement, you are trying to infer from the measurement of physical quantities of different species by means of a law. So in the case of what is it now, a clock, like I just mentioned. In the case of a speedometer, you know what a speedometer is. The case of a speedometer, you want to measure the speed, maybe the speed in your vehicle. It actually has some components that has already been attached to the wheels of the vehicle. Okay, so depending on how fast the wheel rolls, then we try to develop a system that can actually convert how fast the wheel rolls to actually measure the eventual speed of the car, okay, based on how fast the speed rolls. So based on that conversion, then you have a speedometer in the car that actually reads out that. So there's a law, there's a relationship or an equation that relates what you measure here or what you observe here to what is being measured directly from the component that has been attached to the wheel of that car or any other system that is directly attached to the wheel. All right, so that is indirect measurement. So in the case of direct measurement, you are comparing the same species side by side. So you're placing them side by side, and based on the sizes you can observe, you're able to tell that, okay, well, this is what this is compared to this. So that is that about that. So now we talk about what we're talking about, the fundamental quantities and the derived quantities. In this material, it is also referred to as derivatives or derivative quantities. The fundamental thing or the key word here is the fact that it is or they are being derived from the fundamental quantities. So depending on the material you are using, there are 9 or 7 fundamental quantities, but we will have to stick with the ones that have been observed here. All right, we have to stick with the ones that have been observed here. So I'll list them out here and we'll discuss each one after the other. We have what we call the length. Okay, length is a fundamental quantity, mass is a fundamental quantity, time is a fundamental quantity. We also have absolute temperature. Okay, we will discuss them one after the other for you to understand what these things mean. We have what we call luminous intensity. Then we also have what we call amounts of a substance or quantity of substance. Amount of a substance. We have what we call the electric current. Electric current. Electric current. Okay, I guess that is all that have been observed here. Yes, that is all that have been observed here. So we have 7 of them here. 1, 2, 3, 4, 5, 6, 7. So in some materials, they also talk about plane angle and solid angle as being fundamental quantities. Plane angle that is measured in radian, solid angle is measured in steradian. But I guess you don't have to worry about that. Yeah, the reason some textbooks like this one that the lecturer or your professor may have used is some of them do not recognize radian as fundamental because it may be so some of them see it as being unitless, so it is not exactly quantity to worry about. But all the same, just focus on these 7, okay, understand what they mean. So in the case of length, we are actually talking about distance between 2 points, okay. That's what we mean by length. So in some cases it can also be called distance. So it has its SI units. So when you talk about SI units, it means Systema International. It's actually a French thing. I don't think that's what you have here, but it simply means International Systems of Units. Okay, it is not the SI in the first place. The SI unit, SI itself is not an English acronym. It's actually French. Okay, Système Internationale the unit, something like that. Okay, so the SI unit, that means the International System of Units. That means it is the unit that is internationally recognized. Okay, so for length, that unit is meter. Okay, METRE or METR, depending on which English you are using, whether it's American or British. Okay, I think what they are using here is METER. METER, also denoted as M. That's the unit. Okay, and that of mass is kilogram. Okay, kilogram. The unit of mass is kilogram, denoted as kg. The unit of time, SI unit now, is seconds. Okay, denoted as S. The unit of absolute temperature is Kelvin. Okay, measured in Kelvin, denoted as K. The unit of luminous intensity is candela. Okay, and it is abbreviated rather as I mentioned. You can abbreviate it as CD, and in some cases it is also abbreviated as CN, but I think CD is what you are using here. Amount of substance is measured in mole, just like the amount of substance you have learnt in chemistry. Okay, abbreviated as MOL. Electric current is measured in ampere, and it is denoted as A, capital A. Okay, so those are the units. So how did scientists come about all of these things? Like, nobody can just wake up and say, oh, this is a meter, or wherever you see it, this is what a meter is. So we should be able to tell that, we should be able to quantify, we should have an idea that from so length to so length is what a meter is. Just like, I don't know if you have experienced this before. Okay, like I used to have my uncle's wife. If he wants to measure, if he wants to measure a yard of a material, he doesn't actually use tape rule, because over time she has seen that arm length, with her arm she can actually measure it accurately and say, okay, this is what a yard is. Maybe after 2 arm lengths or whatever. I don't know how she actually does it, but she will be able to accurately give an estimate, so to speak, not an accurate one. Give an estimate of what this particular material is, whether it's a 2-yard material or 3-yard or 4-yard. So why she's able to do that is because she has been able to get a standard of measurement. So in that case, arm or arm length in that case is a sort of standard of measurement. So if you want to actually measure something, there has to be standards of measurement. Standard actually refers to a particular object that has been universally agreed upon as a unit, a particular unit. For instance, when you talk about meter, there has to be a standard such that I know that anywhere I am in the world, something that is as long, or something that is between this length and this length, is what a meter is. So if we actually have that standard, then if I want to actually make a measuring instrument, like I want to make a ruler, it has to be directly compared with that standard, or it has to align with that standard, so that I will know that whatever measurement I make with this ruler is correct. What do I mean by that? Okay, for instance, in the case of kilogram, we still talk about others, so all of them are in this material. In the case of a kilogram, we have a platinum iridium cylinder. So the platinum iridium cylinder is a particular material. Its weight is, or its mass is 1 kilogram, and it is kept in Sevres in France. I don't know if that's the correct pronunciation. It's in French. Sevres in France, in Paris. Okay, so it is kept in the International Bureau of Weights and Measures there. So why it is kept there is it is kept under some special conditions. Why? Because if I say that from this point to this point is a meter, again, I also know that this pen can actually be exposed to different conditions at different times. For instance, today it may be hot, and tomorrow it may be cold. For instance, the average temperature today may be just 20, 25, 20 degrees Celsius. The average temperature some other time at some other location may be minus 18 degrees Celsius. So between those temperatures, this one will have expanded and contracted. So it means if I continue to use this as the standard, if I want to actually calibrate another measuring instrument, I'm most likely going to make a mistake, because this may be longer than I originally intended or shorter than I originally intended. So that is the reason why standards are being used. So for the case of kilogram, now I have a platinum iridium cylinder that has been kept under special conditions in France. Okay, so all over the world, if anyone has issues with their meter measurements, maybe they think they are beginning to get errors compared to what others are measuring, they can actually easily go there and compare with that standard measurement and actually recalibrate their own instruments. Do you understand what I mean by that? For instance, a kilogram, maybe you get a kilogram, what do you call it now? Beam, is it beam balance? chemical balance, the one that is usually used to measure stuff. You want to get stuff in the market. Okay, if you find out that it's actually not giving you a correct measurement, what do you have to do? You can get a standard. Let's say you know standard weight. That's what they actually use when you go to buy nails. I don't know if you have gone to where they sell nails before, where they actually use a beam balance. In that case, you have something like this. You have a platform like this, then you have something like a pivot at the center, and then you put the standard weight here. Okay, let's say that I want to buy nails of 1 kilogram, so they put a 1 kilogram standard weight here. It may be a single standard, it may be two, maybe each one of them is 0.5 kilogram or 500 gram. So you put that here. So this one will tilt this way. So they will now pour the nails on this other side, so that when the total weight of the total mass of the nail is now up to 1 kilogram, it will eventually move this up, and this thing will balance. So when it balances, I will know that yes, what I have here is of 1 kilogram mass. That's an example. That's a beam balance, for instance. So in that case, they have used a standard, so that we will know. That means they have a standard. They will always compare these measurements to whenever there is need, so that we can get an accurate measure of what we are trying to quantify. All right, so that's the use for standard. So each of these each of these units actually have their standard. That is, when I say a meter, how can I know what exactly a meter is? For instance, if I'm just new to the scientific world today, how can I know what a meter is? How can I be sure that the meter I come across is the universally agreed standard? So that is why we have these fundamental definitions of this unit. So we look at their fundamental definitions one after the other. The meter, for instance, is defined as the distance that light travels in a vacuum in a 1/299792458 of a second. Well, that is some story right there. Quite some story. Alright, so let's see. This is what we're trying to say. The speed of light. Okay, we will still get there. I think it's one of the topics you will do in this course. The speed of light, or any electromagnetic wave for that matter, is I don't know if you have done this before. It is usually approximated as 3.0 times 10 raised to power 8 meters per second. That's the speed of light. Any electromagnetic wave, whether it is radio wave, or what do you call it, gamma ray, whatever, any electromagnetic wave has the speed of light. So, but this is an approximate value. Its actual value is what has been put here as 299,792,458. This is like 2.99792,458 times 10 raised to power, this is like 0.0. So when I move this 1 2 3 4 5 6 7 8, so times 10 raised to power 8, so that's what has been approximated to this. So this is the speed of light. So because we know that light is light anywhere in the world that you are, so light is light, or any kind of electromagnetic wave, so they will always have the same speed. So then this is a good means, or a good way to actually quantify how long 1 meter is. So that is why it has been used as the standard of measurement in this case. So we are saying that the speed of light is this meters per second. So that means in 1 second, light will cover this distance. Okay, so that means that 1 meter will then be 1 over. Oh, do you understand what we're trying to say? I'm saying that, okay, in 1 second, okay, in 1 second, light will travel v meters. Okay, so that means v meters, or let's say 1 meter, will be what light goes through in 1 over v seconds. All right, I hope you understand that. It's something like I'm saying that within 1 second, if I say within 1 second, I'm going to travel 3 meters. Okay, that means let me say within 1 second, I'm going to travel 2 meters. That means 1 meter is how far I will go in half second. Does that make sense? Like, okay, I know that within 1 second, Okay, I'm going to travel 2 meters. That means within 0.5, which is half of a second, I will have traveled um what did I just say now? I said within 1 second, I'm going to travel 2 meters. That means in 0.5 seconds, that's half of this, I will have traveled 1 meter. Okay, you get that? So how do I come about this 0.5? It is the same thing as dividing 1 by this, which is 2. So I'm saying that if I have a speed of 2 meters per second, okay, that means 1 meter is the distance I will have traveled in 1/2 seconds. So that's the idea with this thing. So I know that the speed of light is 2 point blah 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 times 10⁸ meters per second. So that means 1 meter is the distance that light will have traveled in 1/2 299,297,92458 seconds. So within this second, this is a very tiny second, this is how far light will have traveled. So that's the universally agreed standard for measurements of a meter. All right, so that is the measuring standard. Okay, this one does not have to use a prototype that will be kept anywhere, because light is the same thing anywhere in the world you're observing it. All right, so previously, okay, you have it also in this material. Previously, the standard was the length of the platinum iridium cylinder, or the platinum iridium bar, the same I mentioned, that is still being used as the standard for a kilogram, okay, which is kept in International Bureau of Weights and Measures in Sevres. Sevres is a place in Paris, in France. Okay, it used to be the length of that bar that was used as the international standard. Okay, but now because this is a more easily accessible standard, that is why it is being adopted instead of that one. All right, it doesn't mean that that one is no longer correct. It simply means that because this is a more readily available, universally available standard, so it is better we use this, something that everybody can easily get around them. Okay, so that is that about the standard for meter. So that's how we define 1 meter. Then we have for a second as well. So that what is actually 1 second? So 1 second is defined as the duration, that is the length of time. I've told you what time is. Time is interval between two events. Length is distance between 2 points. Okay, time is the interval between 2 events. All right. Second is defined as the duration of 9,192,631,770 periods of radiation corresponding to the transition between two hyperfine levels of the fundamental state of the cesium atom 133. It is the 86,400th part of the average solar day. This one is strong. Okay, so that is the standard for the second. Okay, it is the duration of 912 blah blah blah. So saying this is a second. The second is the duration of 9,192,631,770 periods. You know what period is? Can you tell what period is? Period, when you're talking about waves, or when you're talking about oscillations generally. Okay, period simply means the time taken to complete an oscillation. Okay, for instance, if I have a simple pendulum, okay, you know what a simple pendulum is? If I hang, let's say I have this as a ceiling, and I hang a rope to that ceiling, then I attach a ball here, then I bring the ball to this position, then I release it. Then it's going to go this way, go to and fro, to and fro. So when I release it and it goes this way and returns here, that means it has undergone an oscillation, a complete oscillation. So the time it took to undergo a complete oscillation is what we call 1 period. So in this case, now we are now talking about the transition between two hyperfine levels of the fundamental state of the cesium atom 133. Okay, so when it has completed this number of periods, okay, we say that it has completed the second. That's like the international standard. I cannot give you details of this because I do not have I do not have a comprehensive knowledge of what is meant by this transition of element. I think you should know that from chemistry. But what's important is you know the definition. I don't think there's any need to cram this. Just know it has to do with hyperfine levels of the fundamental state of cesium 133 atom. All right, and it is the 86,400 path of the average solar day. All right, so you know what is meant by 86,400 path. That means when you divide the average solar day by 1,086,400, okay, you are going to have a second. Okay, that's like where's my calculator? That's like you have 60 times 60 times 60 seconds make a minute, 60 minutes make an hour. So you have 24. So it's going to give you 86,400. You know how you came about that now? I mean, you don't need to cram this. You know that we have 24 hours in a day. That's what they mean by an average solar day. Okay, you have 24 hours in a day. You have 60 seconds. 60 minutes in each hour, and then you have 60 seconds in each minute. So the total number of seconds you have in a day is going to be 60 times 60 times 24. I hope you get that. I mean, there are 24 hours in a day. There are 60 minutes in each hour. So the number of hours will be 60 times 24. Then there are 60 seconds in each hour. So the total number of seconds, 60 seconds in each minute. So the total number of seconds will be 60 times 60 times 24. So we have 86,400 seconds in a day. That means 1 second can be quantified as 1 over 86,400 day. So that's what that's what is meant by a second is the 1 over 86,400 part of the average day. Whenever you come across something like that, it's just like saying if I tell you something like the length, I can say that the breadth of this calculator is 1/3 the total length of this ruler, okay, or I can call it a third. Okay, so if I call it a third, that means I'm simply implying 1/3 of that thing. So when they call it the 86,400th, so that position is to tell you that it is actually 1 over 86,400. Do you understand that? Of the total duration of a solar day. So an average solar day. So that is what it's meant by a second. So you can use either of the standard. So you should just know it. So I think this one is more relatable compared to the other one. So that's the standard of measurements for a second. All right. Then in the case of the kilogram, when you talk about a kilogram, we say that I've mentioned it before, so it's good for saying it now. The international prototype of the kilogram, a cylinder measuring 39 millimeter in height and diameter, consisting of an alloy of platinum and iridium, is stored in the Bureau International du Poids et Mesure. That's in French, International Bureau of Weights and Measures in English, okay? That's in Sevres, Paris, in France. All right. So that is 1 kilogram. So that's international prototype of the kilogram. So in this case, we don't have a generally relatable quantity for it that anybody in the universe or anywhere that you can easily get and use anywhere in the universe. That is why the prototype still has to be retained. In the case of meter, you can easily get that by looking at the speed of light, but in this case you cannot easily get that. So that is why the prototype is still being used. So the a kilogram is the mass of a platinum iridium cylinder whose prototype is kept in Cephas in the International Bureau of Weights and Measures. So that means if I want to construct a, what is it now? If I want to construct a beam balance or chemical balance and I want it to be very, very, very accurate, I can go ahead to that Bureau of Weights and Measures and have my instrument originally calibrated there, so I know that what I'm doing here is very, very accurate. You know that there is always human error, there will be errors due to human observation, due to the expansion and contraction of measuring instruments and all of that. So that is why that prototype has to be kept under special conditions. I've said that before. So basically, what I'm trying to say is that if somebody now goes there and calibrates their instruments originally from that place, and then they bring it to, let's say, Nigeria or to Italy, and from there, maybe you now have in Italy a national bureau of weight and measures, and from there scientists from different parts of the country will come to actually also standardize their instrument. As the link of that standardization and use of that standard goes on and on and on, there's going to be a reduction in accuracy. So that is why the original prototype has to be kept somewhere, so that if in an eventual case that of when you begin to observe a major discrepancy between measurements, you can easily go back to the original source and recalibrate your instrument. Okay, so I guess that is that about that. All right, that is that about that. So those are the fundamental quantities. So another thing we'll talk about now, we have only talked about length, mass, and time. Those are the basic fundamental quantities, the commonest fundamental quantities you will always come across: mass, length, and time. That is why it appears that we only have standard for. We have standards only for this. There are also standards for others, but you do not have to worry about that. Okay, for now. All right. So you should actually just know that of length, mass, and time, like we have discussed. All right. So the next fundamental quantity we have is absolute temperature. So when you hear temperature, you know that normally you can measure temperature in degrees Celsius or just Celsius, whatever you call it, or degree Fahrenheit or just Fahrenheit, or degree Rankine or just Rankine, or Kelvin. All right. So when you hear the word absolute, when used with temperature, it simply refers to the Kelvin temperature. That is, absolute temperature is temperature measured in Kelvin. Okay. For instance, when you are talking about the gas laws and you are stating the gas laws, for instance, you talk about Boyle's law. The volume of a given mass of a gas is inversely proportional to its pressure, provided that its temperature is kept constant. Okay. Or you state another one, is it Charles law? Okay. For all of those laws, whether you're talking about pressure or you're talking about temperature, the temperature there always refers to the absolute temperature. So there are some cases where you're expected to actually put the word absolute, okay, for your definition to make sense, because it has to be measured in Kelvin for those laws to hold. Okay, if your temperatures are measured in another quantity, for instance, you are going to get a wrong answer, because the laws were originally stated for a situation where the temperature is measured using absolute scale or the Kelvin scale. Okay, so absolute temperature refers to temperature measured in Kelvin. Okay, and with this, the lowest possible temperature, the lowest theoretically possible temperature is 0 Kelvin. That's minus 273.03 degrees Celsius. Okay, so our 0 degrees Celsius is 273 Kelvin. Can you imagine? All right. So don't worry, when you get the temperature measurements, you know more about this. But just know that the absolute temperature is a fundamental quantity and it's measured in Kelvin. Then we have what we call luminous intensity. Okay, in this case, we talk about intensity of light. For instance, if you want to measure it, you know what luminous means now, from luminate or illuminate. You know it has to do with light. Okay, so it's something like light intensity is measured in candela. Don't think you will ever have to use this, but just know it. Okay, then we have amount of substance. I think you already using that, familiar to that. Amount of a substance is measured in mole, as defined in chemistry, so it is here also. I don't think you will have to use this in physics, but just know it. All right. And electric current, you use this a lot in physics. Electric current is measured in amperes. Okay, in honor of the scientist that first, is it came up with it or just first worked with it? I don't know, but just know the unit is ampere and it's denoted as A. So 1 ampere is 1A, 2 ampere 2A, and all of that. So when we get to electricity, you will understand much clearly what is meant by electric current, how it's measured, its relationship with voltage, and other electric currents or electricity parameters. All right, but for now, just know it is a fundamental quantity and its unit is in amperes. All right, so that is that about that for fundamental quantities. Then there are those we call the derived quantities. Okay, so the derived quantity is, generally speaking, any quantity that is not amongst this fundamental quantity is a derived quantity. I repeat, any quantity that is not part of this 7 is a derived quantity. Now, don't mix it up. Now, when you hear length, mass, time, they would not always come as directly mentioned here. For instance, as we proceed, you will get to see difference between distance and displacement. Okay, distance is actually a form of length, so distance is a fundamental quantity. Okay, when you talk about mass also, you can have another quantity that has a unit of mass. If the quantity has a unit of mass, it is also a fundamental quantity. If a quantity has a unit of time, it is a fundamental quantity. You understand? So I'm not giving a kind of is it blanket classification. So the point is that these are the fundamental quantities and fundamental units. So if you have a quantity, you know its unit, and its unit is neither of this, it is not any of this, then it is definitely a derived quantity. Okay, but if its unit is equivalent to any of these things, it is also itself a fundamental quantity. So it is just equivalent to one of these fundamental quantities. Okay, for instance, distance traveled by an object is measured in meters or whatever other units of time you may have. It is actually a fundamental quantity of length. All right, so another thing is, like I said, these are international systems of units. That is, these are internationally agreed units. You can have other kinds of units for each of these measurements. For instance, I can measure length in inches, I can measure length in centimeter, I can measure length in millimeter. But universally, this is the agreed standard. This is the standard measurement used. Okay, so in some calculations you may have to convert to from one of them to the other. I don't know if you use a calculator. If you use, we will still talk about some of them, but if you use a calculator, there is a scientific calculator, there is always a means for conversion. Okay, at the back here where you can easily enter the parameter and convert. For instance, in this one, I don't know the one you're using. If you are using the same type, for instance, if I want to convert here, I will simply press or use shift 8. When I press 8, you can see conv on it, so it means conversion. So I will choose from 01, from 01 to 40. So they have been listed here. What 01 means? 01 means I want to convert from inches to centimeter. 02 means I want to convert from centimeter to inches. So everything has been listed here. So anyone I want to do, can I put it here? That okay, I have, let me say 01. So it goes from inches to centimeters. So I should have entered it before I started. So I may have 10. So that means in this case I want to convert 10 inches to meter. I'll just put equal to 10 inches to meter. Let me start again. 10 shift conversion 01. So it gives me 10 inches to meter. So I put equal to, so it gives me the result. 10 inches to centimeter rather. So 10 inches is actually 25.4 centimeter. So that's how you can do that. I don't think you need to cram the conversion parameters since you have them on your calculator, and for most cases you will, I think in all cases you'll be allowed to use calculator. If it is not so, let me know so that we will have to look at those conversion skills and see how you can memorize or internalize some or most of them that you will need. Okay, so that is that about that. Again, for instance, kilogram, you can have a mass, you can have mass measured in gram, you can have it measured in, what else is being used, pounds. Okay, you can have it measured in kilogram as we have it here, and so on and so forth. We will see I think in the second lesson we will see powers when you are reporting quantities in powers of 10, other things that we can other prefixes that we can use to actually communicate that. For instance, kilo generally refers to 10 raised to power 3 gram. Okay, so kilogram is actually 10 raised to power 3 gram. That's 1000 gram, but we'll talk about that in a later session. Okay, so anything not part of this unit, these quantities are units, and does not have a unit that is equivalent to any one of them, is a derived quantity. So let's see the derived quantities we have here. So we will have to be converting from one unit to another, okay, when we are dealing with fundamental quantities, and even when you are dealing whether you are dealing with derived quantities or fundamental quantities in measurement and in different experiments and problems, we may have to convert from one form to the other. So to facilitate that, we will usually make use of this. Okay, we usually make use of this conversion, that is conversion of one unit to another. So how can we convert from one unit to another? That is what we will discuss now, discussing derived quantities. So in the case of derived quantities, they have actually been obtained. They are quantities that have been obtained from fundamental quantities by formation of a particular law or relationship between the fundamental quantities. For instance, when you talk about speed or velocity, in this case, they are different, but it is you can be forgiven for implying that they are the same in this case, because they have the same units actually. Okay, so speed or velocity is measured in meters per second, SI units, meters per second. So that means this has to do somehow with you saying speed is equal to maybe something like length over time. Meter is unit of length and second is unit of time. So when you say meters per second, this per simply means meters over second. So meters per second suggests that you came about the speed by dividing a mass dimension by another time dimension. So everything then resulted in this. So this is a derived unit. Meters per second is a derived unit. That tells you that this is not equivalent to any of these ones, but it is actually a combination of some of them. Do you understand? Two, three, or four of them. So it's a combination. So this is a derived quantity. Another derived quantity you can think of is volume. When you talk about volume of a substance or volume of an object, it is actually usually measured in a meter cube in SI units. That means usually you can get volume by taking length times breadth times height. You know that length itself is a length, breadth is a length, height is a length. Do you understand what I mean by that? We're talking about length generally here. Length generally here means distance between 2 points. Okay, so here it is just used as a name to tell us how long the object is. For instance, if I want to measure the area of this, I'll say, okay, this is its length because it is long at this end, and this is its breadth. It is broad, at this with this dimension. This is its breadth. So, but this breadth is actually a length. But that is, by breadth, I'm actually referring to the distance between this end and this end. So this is a length. By length also, I'm referring to the distance between this point and this point. So this is also a length. By height, for instance, the height of this point is actually the distance between this point and this point. So it is actually a length also. So in the case of volume, I'm dealing with three length measurement that have been multiplied. So that means I'll be multiplying. In the case of their units, I'll be having meter multiplied by another meter, because this one also will be measured in meter, multiplied by another meter. So that's how it came about, meter raised to power 3. That's meter times meter times meter. Okay, so this is a derived quantity. It is not equivalent to any of them, but it's a combination of two or more of these. Do you understand that? So you have meter combined in three forms or multiplied 3 times to give you this. So this is a derived quantity. So there are plethora of them. We have a plethora of derived quantities. You can talk about acceleration, which is meters per second square. You can talk about voltage, it's a derived quantity. You can talk about area. Area is meter square. It's also a derived quantity, and so on and so forth. So those are derived quantities. So you may also want to actually express these quantities, these derived quantities, in terms of their dimensions, what we call the dimensional analysis. Okay, so this is what this is how we do dimensional analysis. When you get the quantity, you know its definition. Okay, when you know its definition, you know its unit. So from its unit, in dimensional analysis, we want to establish a relationship between that quantity and the fundamental quantities. For instance, I know that speed is meters per second, and I know that meter is a unit of length. I know that seconds is a unit of time. So what I have here is LT raised to power minus 1. You know what raised to power minus 1 means? It simply means, for instance, when you have t raised to power minus 1, it simply means 1 over t. When you have t raised to power minus 2, it simply means 1 over t square. Okay, so this minus implies that it is meant to be at the denominator. So when you have LT to power minus 1, it's the same thing as L times 1 over t, which is the same thing as L over t. So the dimension of velocity, which I can write as the square bracket velocity, will be equal to LT to power minus 1. I'm simply saying that its unit is the same as the unit of length multiplied by the inverse of the unit of time. That is what we mean by that dimension. For instance, if I want to look at the dimension of volume, I will say the dimension of volume is meters. Okay, normally I know that the unit of volume is meters raised to power 3. So then the dimension of volume, so let's say, let me write this in full so we don't confuse it with velocity. The dimension of volume, or you can say the dimension of volume will be equal to, this meter is unit of length, so this is L raised to power 3. So that means I'm saying its unit is unit of length raised to power 3. So that's the dimension of volume. When you have area, also the dimension of area, area is as unit of meter square, so the dimension of area will be L raised to power 2. That means it's the square of the units of length. Alright, so that's how to get this dimension. When you talk about force and other quantities, let's quickly look at force. For instance, that's the one that may appear tough, but it's actually simple. When you look at force, for instance, how to get force is, we know that force is a derived quantity. So what we ask ourselves is, how was it derived from the fundamental quantities? It's actually typically derived using the Newton's second law. So for now, just know that Newton's second law is force is equal to mass times acceleration. This is a simplistic representation, but it's fine. It serves the purpose here. So we know that acceleration itself is a derived quantity, but mass is a fundamental quantity. That means we need to have actually further break this down. And how we can do that is we can consider the unit of this. The unit of mass is kilogram, okay, and multiplied by the unit of acceleration. Acceleration is usually measured in meters per second square. Okay, I think when we get here you will understand this in case you don't know. So this is multiplied by meters per second square. So the unit of force, although it is Newton, it is actually equivalent to kilogram meters per second square. So our aim in dimensional analysis is that we actually want to write the unit of that derived quantity in terms of the units of known fundamental quantities. Alright, so now I've been able to successfully do that. I've expressed the unit of this derived quantity, which is force, in terms of units of fundamental quantities. Okay, we know that kilogram is a unit of mass, which is a fundamental quantity. Meter is a unit of length, which is a fundamental quantity, and second is a unit of time, which is a fundamental quantity. So I can now successfully say that, or conclusively say that the dimension of force has to do with the dimension of mass. I know that this one refers to the unit of mass, and it is not raised to any power. It is not also in the denominator, so I'm just going to write it here. This one is meter. It is also not raised to any power, so, and it is unit of length. I'll put it there. This one is second square, and this is in the denominator. This means divided by, so I'm going to put it as it. I know it is unit of time, or it is in the denominator and it has power of 2, so I'm going to put minus 2. So this is the dimension of force. This is dimension of force. So that's how to get dimension of different quantities. You try to find the relationship between that quantity and the fundamental quantities. Then you express the units of that quantity in terms of the units of the fundamental quantities. So when you have done that, you can now write, using that unit, you can now write that derived quantity as, or in terms of the fundamental quantities, taking into consideration the powers of their different units. So when you have done this, then you have completed a dimensional analysis, or you have gotten its dimensional equation. Alright, so that is that about that. So in dimensional, we also use this dimensional analysis to verify that an equation is correct. Okay, a correct equation is dimensionally homogeneous. Dimensionally homogeneous. So what we mean by this, you know what homogeneous means? Homogeneous means the same, just like we have heterogeneous means of two different kinds. Homogeneous means of the same kinds. So it means, what this implies is that if I have an equation and I want to verify that the equation is correct, okay, I can perform a dimensional analysis of each of the additive terms in that equation. When I perform that and I establish that each of the additive terms has the same parameter or has the same dimension, then the equation is correct, or is probably or most likely correct. Okay, an example is this. This equation of motion, I don't know if you know this, S equal to ut plus half at square. If you have come across this before, so I may want to verify if this is a correct equation, where S is distance traveled by the object, u is initial velocity of the object, t is the time taken, okay, in its travel, acceleration, a is acceleration of the object. So I may want to verify if this is a correct equation. How do I do that? What I simply do is take each of them. So this is a term, this is another term, okay, this is another term. That's why I said additive terms, that is terms that have been added or subtracted. Okay, basically subtraction and addition are the same thing. Did I just say that? Yes. Subtraction simply means you're adding a positive number and another negative number, so it's essentially addition. Okay, so when I say additive terms, I also simply mean subtractive term. Is there anything like that? No, but we know what I mean. Whether it is minus you have here or plus. For instance, if I move this here to become minus, so it will not change anything. I will still have to examine its dimension, examine the dimension of this, examine the dimension of this. So if their dimensions are the same, then I have a correct equation. Otherwise, the equation is wrong. So that is what is meant by dimensional analysis. Is a tool for verifying the correctness of formulae. Formulae is plural of formula. You can also call it formulas. Okay, so in this case, how will I do that? I know that S here represents a distance. So I know that the unit of a distance is meter. Okay, so I know that the dimension of this one is L. Basically, dimension of this one is L. So I move to the next additive term. The next additive term is ut. So I'll find out what its unit is. U is a velocity, initial velocity. Velocity is measured in meters per second. Remember, so I'll put meters per second. Okay, multiply by time. So time is actually second. So what I have here is meters per second. Meters per second is meter over second multiplied by second. So this second, we cancel this second. So what I have left is meter. So that means this term has the same as a unit of meter or dimension of length. So the dimension of this one is also length. You get that? So I go to the third term. The third term has 1 over 2. 1 over 2 is just a scalar quantity. It's just a number. It does not affect the unit of this. This one is unitless. So I will not bother about this coefficient because it has no unit. I'm just concerned with the units of the actual quantities that I have here, not this multiplier. This is just a scalar multiplier. All right. So I will look at dimension of a t square. So dimension of a, a t square simply means a times t square. Dimension of a or unit of a is acceleration. So acceleration is measured in meters per second square. Okay. And then I have t square. T is measured in seconds. Then t square is going to be measured in second square. So again, this is the m divided by s square, and this is s square. So s square will cancel s square. What I have left is meter. So this tells you that the unit of this quantity is also meter. So its dimension is simply L. So I have now been able to establish that the dimension of this is length, the dimension of this is length, and the dimension of this is length. So with this, I have verified that I have a correct equation. No, as far as dimensional analysis of is concerned or is able to establish, and I can say this is correct. That does not mean that this is actually correct, because there may be a wrong coefficient here, but dimensional analysis cannot establish that. Dimensional analysis can only establish based on the dimension of the quantities whether or not the equation is correct. So we can say with 100% certainty, if the dimensions are not the same, the equation is absolutely and certainly wrong. But if the dimensions are the same, the equation is probably correct, because of course it will depend on other verifications. But if the dimension is the only thing, or dimensional analysis is the only thing we have or the only thing at our disposal, of course this equation is correct based on that. I hope I have not confused you with my use of words. Alright, so you can do the same thing for other equations that you know and try to verify if they are correct. For instance, we have the Newton's law of universal gravitation. So you can take it as an exercise. Newton's law of universal gravitation says that the force of attraction between any two objects in the universe is directly proportional to the product of their masses, m1, m2, and inversely proportional to the square of their distance apart, r square. So this r refers to distance, okay, the distance between the centers of the object, and m1, m2 refer to the masses of the object, the respective masses of the object. F is the force of attraction between them. So based on this, what unit or what dimension does G have to have? So what is the dimension of G that will make this equation correct? So you can find out. Try your hands on this. Again, can you verify that this equation is correct using dimensional analysis? We have that V square is equal to U square plus 2a, and we have V square is equal to U square plus as, and we have V square is equal to U square plus 2s. So based on or using dimensional analysis, which of this is correct? Which one is correct? So you can try your hands on this and try to find out which one is correct. Where V is final velocity, U is initial velocity, A is acceleration, and S is distance traveled by the object. So I think with this you should be able to deal with every other problems that you may have in lesson 1. Okay, that is that about that. All right, so try your hands on the orders that you have here and also see if you are able to establish it. For instance, this material also talks about energy, or in this case E equals mv square. So based on this, can you obtain the dimension of energy? So try it out with what we have done here. We also have potential energy. Okay, potential energy or potential. Okay, So you can take its formula as P is equal to mv square all over T, okay, where V is velocity, this one is mass, this is velocity, this is time. All right, so with this, can you find out what the dimension of potential is? So you can do all of that and try to find out, so that will tell if you have understood this or not. Right, I guess that is that for today. Thank you.